Good morning, everyone. Thank you for being here. It's exciting to be here at PyData Carolinas. Thanks for coming to our tutorial. We're going to be talking about doing social network analysis in Python using the NetworkX library. My name is Peter Baumgartner. I'm a data scientist at RTI International, literally right across the street here, which is a nonprofit research institute. We do a bunch of awesome stuff. This is my pal, Rob. Rob, introduce yourself.
All right. Hello, everyone. My name is Rob Chu. I'm also a data scientist at RTI International. Peter's going to be doing the first couple, so I'm going to hand it back to him, but not to worry, I'll be back on stage soon.
He'll be back. His jokes are better. Okay, so the easiest way to get started here, to follow along with the presentation, you can, of course, follow along with the slides presented up here. We also have a GitHub repository, which you can clone. There is a conda environment file in there, which will create an environment for you that will contain all the packages and the right versions of those packages to follow along. And there are also notebooks, which these slides were generated from. So if you want to follow along and execute the code yourself, that would be the best way to do it. Those 4 commands are up here if you're unfamiliar with conda environments. Great way to package similar to virtual environments if you're familiar with that. All right, so we're going to be talking about social network analysis. We've broken it up into sort of 6 different ideas. We're going to give some background, some motivation first. We're going to talk about how to create graphs in NetworkX, how to visualize those graphs, what is centrality or the idea of importance in a graph. We're going to do some link prediction, and then finally talk about community. We've got 90 minutes. We want to leave about 10 minutes for questions here, so we do have some stuff we can cut out if we end up going a little long here. Okay, so for the first section, we're going to talk about what is social network analysis. I want to cover some examples first. We have 3 wonderful examples to go over here, and then just go over some definitions and vocabulary. As data scientists, I hope you'll agree that a lot of times the hardest thing to learn is figuring out what words and vocabulary people use to talk about things. It seems like there's no one has stepped forward and decided to define these things in a consistent manner. So I wanted to just go over some vocabulary and definitions so we can be sure that we're using the same vocabulary when we're talking about networks. So here's our first network. This is called the Zachary's Karate Club network. And this is a really cool network. I call it the Iris dataset of social network analysis. Basically, anytime there's a new algorithm or library or something that does social network analysis, it will do it on the Zachary's Karate Club network. So from this network, you'll see a few different things. Basically, you've got objects, and those objects have connections. We call those objects typically nodes or vertices, and the links between them we call relationships, edges, links. There's a ton of vocabulary. But this network specifically, what we're looking at is 34 members of a karate club, and the sociologist Wayne W. Zachary took a look at the members of this karate club, and he recorded their interactions outside of the karate club. Not that interesting in itself, but what ended up happening was that the karate club split after 2 of the leaders got in an argument, and what he was able to do is predict which separate karate club the members would go into based off of their interactions outside of the karate club. So that's what you see here. The pink nodes here went into one karate club after the separation, and the white nodes went into another karate club after the separation. So Zachary was actually able to predict all of these memberships correctly except for one based off of a link flow algorithm, which we're not going to go over, but it definitely shows the power of data analysis on graphs and a real-life application of this. So another interesting graph is this graph here. We're looking at families in Renaissance Italy, and so those are our nodes, those are our objects, and they get tied together if there was a marriage between those 2 families. And from here, what's of critical importance, I know this font is kind of small, but is the Medici family. And what actually ended up happening was the families that were the most powerful ended up being the most powerful because of their connections, not because of their wealth or necessarily their political ambition, but it was sort of like how far they had spread through this network of influential families. So this idea of importance, we see that the Medici family is the most connected, is this idea we call centrality, and Rob's going to cover that. And finally, this graph isn't social network analysis, but it is network analysis. And one idea I want to convey is the fact that social network analysis is just a subset. It's a specific way of analyzing things when you're dealing with people and social interactions. Here you have a network where your nodes are actually words, and they are linked together if the words co-occur in a section of text. So these people took a body of text and they drew relationships between words if they appeared within 2-word and 5-word windows. And then what they actually did, you can see a little bit of coloring in here, is they actually ran a community detection algorithm, which we'll also talk about. And from that, they did something sort of like topic modeling. They're able to look at which groups of words occur together and also get sort of a nice visualization. I kind of call this the word cloud on steroids. A nice visualization of what the semantic meaning of that text is. So I really want to get across that networks don't always have to be dealing with just people and social relationships. Anytime you have objects and you can think about how they're related, you can make a network out of that. And that's one of the things that I think makes network analysis in general really exciting, is that it gets you in the habit of thinking about your data or what you're looking at in different ways. Okay, so just some definitions. I've hit on some of these things already. A network, the best definition that I could find is just a pattern of interconnections among a set of things, not even dealing with social interaction yet. A social network is a specific network where the things are people and their interconnections are social interactions. So that could be on Facebook. If 2 people are friends, we could call that a social interaction. Social network analysis is the application of graph and network theory to investigate social structures. Graph theory, if you think about this on a spectrum, graph theory is like the very rigorous mathematical way of understanding networks. So from the mathematical sense, we call networks graphs, and we'll see that come up. NetworkX uses the term graph to deal with networks. So on the formal mathematical end, analysis of these structures falls under graph theory. And more on the softer social science end is network theory, and that's just the study of interacting systems or networks in general, without necessarily the mathematical rigor you would expect from graph theory. Right, so parts of graphs, again, I've briefly mentioned all these in our examples here. Most importantly is the node or the vertex. That's the object that you're dealing with. So in a social network, these are people or actors. They are the things that have relationships, but they aren't the relationships themselves. In network analysis context, we usually use the term node. That's what NetworkX uses. And if you do something that's leaning more towards graph theory, you'll see the term vertex a lot. I've worked with libraries that use both terms interchangeably too. Links, edges, or relationships are the things that connect the nodes. In the network context, we usually use the term link. Edge is used more commonly in graph theory, and all 3 of those words are used interchangeably, and you throw relationship in there too. So we've really got a soup of vocabulary here. Both nodes and edges can store attributes, which are just additional information about that object or that relationship. So in this sort of toy graph over here, the nodes are also storing an attribute that's their node color. So in this case, we've got a color which is green. Weight is a common attribute of edges. You can use weight to indicate strength, value, or frequency of a relationship. So here we've got 2 edges. This one has a weight of 2, and this one has a weight of 5. This one you could say is stronger. That's important because different algorithms handle edge weights differently. And finally is degree. We'll see that come up briefly, but degree is just the number of edges or relationships a node has. All right, and as a final piece of vocabulary, we're almost to the good stuff. Graphs come in many different flavors, and when we talk about graphs, it's important to clarify what type of graph we're dealing with. The analysis and algorithms that we use will have different results depending on the attributes and properties of that graph. So most commonly, we can refer to graphs depending on their directionality. So if direction is important, a graph is called a directed graph. So, for example, 2 people being friends on Facebook is undirected. There's no relationship, directional relationship involved there. But in comparison to Twitter, you have people who can follow you, where that would sort of be a directed edge towards you as a person, and people you follow, which would be a directed edge outward from you. So directed and undirected graphs can be thought of in similar ways, but it's important to just think about whether directionality is an important factor in how you're representing your network. The other important thing to think about is weights. So the previous example graph was a weighted graph. We saw that our edges did have weights associated with them. We can also deal with an unweighted graph, or another way to think about that is that the edge weights are either ones or zeros, just a binary indicator of whether a relationship exists. There are some additional flavors you might see added on top of this. You can have parallel edges where the edges can be more than one type of relationship. You can have self-loops where nodes link to themselves. And you can have n-partite graphs, which means that you have two different types of nodes and you're trying to understand relationships among several different types of objects. So in context, we would say something like we're talking about an unweighted directed graph with parallel edges and self-loops, something like that. And again, I really just want to hit home that a network is really just whenever you have a set of objects and relationships. It doesn't have to be people. It can be anything that you can conceive of within that structure. All right, so what better way to wake up at 9 in the morning than to start doing some Python? So we're going to get to the good stuff now. Creating graphs in NetworkX. We're going to use the NetworkX library. It's a library for dealing with networks and graphs written purely in Python. It's really nice to get started with and learn from before you advance on to more complicated libraries. So we're going to deal with creating a graph object. We're going to add nodes and edges to that graph. We're going to add attributes to those nodes and edges. And we're going to look at how to load in several different data types. You'll see this typical set of imports for this kind of thing. We're going to use the CSV package just to read in our network data from a text file. Yes, so if you, there is a repository with the notebooks and slides. So the repository is under the RTI Data Science user, and it's the connected NX tutorial repository. And once you're in here, there's a notebooks folder. And the IPython notebook files will correspond to each of these topics here. It'll load in here. Oh, yeah. So these are the notebooks. These follow along pretty much one-to-one with the slides. If you want to view the slides, you can use a website called nbviewer. So that's nbviewer.jupyter.org. I'll show you that really quick. And from there, you can copy in the repository name and access the notebooks and the slides from there as well. So if you copy paste that in and you click on a notebook, you can click this little gift icon up here and it will also bring up the slides that we're looking at too. Anyone having any issues with that? Yes, sorry. I'll do this. Too big. So if you go here, the notebooks themselves are in the notebooks folder. And if you want to view the slides, you can view them through NB Viewer, which I will link to here as well. You can just copy paste in the repository. Clarification question. All right, everyone mostly set? Mostly set? 90%? So sorry, yes, I should have clarified that. I had it on the first slide, but good to check that everyone's able to access it. So yeah, if you want to go to the slides, if you load it into NB Viewer, you can click on whichever notebook we're on, and then this little present icon will view the corresponding slides as well. I would just view it through the notebook. It follows along exactly with what we're doing too, and there's some supplemental information in there too. All right. I wonder if... Nope. That doesn't work. That's a bummer. You know, it may be better to just go through the notebook and see if I can bump up the notebook size. Aha. All right, we may do that. That may be easier to present with. All right. That's easier to see, right? Okay, so I'll go through the notebooks so we can get the visual here too, so it's not too small. The notebooks and the slides are pretty much one-to-one. There's some additional information in the notebook, so if you see a bunch of text, I may not cover it in the notebook, but this way we'll be able to see what's going on here. Okay, so typical libraries we're going to use for this. We're going to use the CSV library just to import our data from a text file. We're going to use the NetworkX library, import it as NX. We're going to import Pandas, data analysis library as well, and matplotlib, pyplot. If you do data science, you are very familiar with two of these. All right, so to create a graph object, we are just going to use the graph constructor from NetworkX. You create a NX graph here and store it as G. In all the examples, you'll see graph stored as just a capital letter, typically G. From that graph, we're just going to call methods on that graph to add nodes. So one way to add a node is to just use the add node method. And what you're going to pass to that is the label of that node. So in this case, we're just going to add a new node. Its label is just the number 1. If you have several nodes you want to add, you can use the add nodes from method. Here we're just going to pass it a list of node labels. So here we're passing it 2 and 3. And just to have something to take a look at, we're going to add another node here. So we've created a graph with 4 nodes at this point. We validate what nodes exist by calling the nodes method on G. That'll give us a list of all the nodes. One important note here, if you begin to use the next version, the development version of NetworkX, I'm not sure when that will be totally stable, but a lot of these methods return iterators, so you won't just be able to call nodes and get the list right out of that. You have to call a list function on it. So we have a graph with some nodes, but we don't have any relationships. We don't have any edges. So to add an edge, we just use the add edge method, and you pass it the 2 labels of the nodes that you want to draw an edge between. So here we're going to draw an edge between node 1 and 2. And we're going to take a look at the info from this graph. So we can use the info function. We'll pass it our graph, and it gives us a string. So we're going to print out that string. And it's going to give us some details, basic details about our graph. So we've got 4 nodes. We have 1 edge contained in our graph. And it's going to tell us the average degree. So 2 nodes have degree 1, 2 nodes have degree 0, average degree 1/2. Let's draw the graph just to take a look at what we're looking at. This graph isn't very interesting, but we do have a whole section on graphing that will allow us to look at graphs in a little more detail with a little more complexity. So the draw method, you pass it a graph. We're going to also add the with labels option to get our node labels in there as well. All right, adding and inspecting attributes. So you can add attributes to nodes at creation. So for example, here we're adding a new node. We're going to add the label 5, and we're just going to pass it kwarg style. We're going to say favorite color is blue. So we're adding a new node. Node 5's favorite color is blue. You can do the same thing with the add nodes from method. This time you're going to pass it a list of tuples, where the first item is the node label. The second item is a dictionary of attributes for that node. Similar style happens with the add edge. You still pass the 2 edges you want to, or the 2 nodes you want to draw a relationship between, and you pass it an attribute dictionary that has all the attributes with that node or with that edge. To access the attributes, you use this node. It's an attribute. You call it like a dictionary. So we want all the attributes of node 5 and print those out. So node 5's attributes. We just have favorite color is blue, just like we said. Calling attributes of edges is done in similar dictionary notation. This, with an undirected graph, it doesn't matter in what order we pass these, so we could ask for the edge between 5 and 6, or 6 and 5. We get the same information back. All right. Oftentimes we'll have supplemental information to our network. We'll have a data set where we have a bunch of information about each node in our data set, and we'll want to add that information to the network so that we can add it as covariates and begin to analyze it. So here we've got a data structure. It's just a dictionary. It's an attribute dictionary where the key is the node label and the value is the attribute that we want to add. So here we've got some made up favorite foods for our arbitrarily labeled graph. Once you have that dictionary, you can use the setNodeAttributes method, and what you're going to pass there is the graph. You're going to pass it what you want to call that attribute once it's added to your nodes, and then you're going to pass it that attribute dictionary. Once we know that, just to validate, we're again going to use that dictionary notation. We're going to say, give me node 4 and give me the favorite food attribute from there. And good old node 4, their favorite food is pizza. Fantastic. All right, so reading in different representations of graphs. Graph data can come in many different formats, and a lot of time it's a bigger challenge to get your data in the right format so that it can be imported into a graph. So we'll cover 2 different ways that graph or network data can be represented and how to import that, but know that there are many others like adjacency lists or incidence matrices. We've got some stuff in the appendix notebook to cover that, but graph data can be represented in many different ways. And as an important note, that's separate from how it's stored. So you can store it as a text file we'll read in. You can take a graph and store it as a GraphML object or a GEXF file or a JSON object. The structure of the data is different than how you might store it. All right. Here's our data set. We're looking at characters from the hit drama Grey's Anatomy on ABC. And our network here is a social network where the characters are our nodes and the edges are the romantic encounters among the characters in the show. So let me first talk about edge lists. They're a common way of representing the graph. You can just think about it as a list of tuples or a list of 2 nodes. And all that means is that there's an edge between those 2 nodes. It's probably the simplest way to represent a graph. So what does one look like? Here we've just got it stored in a CSV file. The CSV just has a header row that's saying, the edge is going from this character to this other character. And here's what that looks like. So we've got an edge between Lexi and Sloan, all the way down to Derek and Gray. This is just using the head shell command to get a look at this text file. From here, we can also infer what all the nodes are if we just take the set or the unique values of all of our different edges here. So this can contain all the information you need to build a graph just in the edge list here. We're going to read this in with the CSV library. This is a pretty common pattern. The one thing we're going to add here is just use the next on this iterator to skip the header row. So we don't want to read in the header row because it's going to add from and to as nodes in our graph, which aren't actually nodes. And we're just going to make a list out of all of these edges. So once we read that in, here's what the first 5 of those edges looks like. So we've taken our text file, we've imported it into a Python list. And NetworkX has a nice function just called fromEdgeList, and it will create a graph object from your edge list. So here we're going to store our graph as GA, Gray's Anatomy, Graph Anatomy, and we'll see it referred to GA a lot of times throughout this presentation. So whenever you see that, know that we're referring to this graph that we've just imported here with all the characters and their relationships. We're going to use print and the info function again just to get some basic details about this graph. So this graph has 32 characters we're looking at. There are 34 relationships, so we know that they're definitely not monogamous. And the average number of partners is 2.12. So even from this basic information, we can infer a lot about the graph. I think, if you're looking at these characters, if you had only heterosexual relationships and they all only had one relationship, you would expect 16 edges, right? So we know that that's at least double that. So you're not exclusive necessarily if you're a character on Gray's Anatomy. As a little sidebar here, oftentimes you'll be working with data in Pandas. And I just want to cover, NetworkX has a nice function to import that data from Pandas as well. Basically, this just avoids the issue of having to read in through the CSV library and skipping that header row. If you're doing data analysis, it's pretty common you're using Pandas, so I just wanted to cover this really quick. So for example here, we've read in a CSV into a data frame. Just going to print out the head of that data frame. It's the same data, just represented as a data frame object now. And we can use this from Pandas data frame method. And we're going to pass that the data frame. And all we have to do is call out which column is the source column and which column is the target column. So here we've labeled it from in the data set and to in the data set. Again, with the vocabulary thing, you'll see source and target a lot with edge lists. You'll also see from and to. There's many different ways to think about it. And also keep in mind with an undirected graph, this order doesn't matter. So it could be Sloan and Lexi switched on for the top row here. Just going to print out that info to validate that we're dealing with the same graph. We get the same statistics in here. So it did import correctly. Here's our first view of the graph. We have a whole section on drawing, so don't get too caught up with this. We're just going to use the draw method on this graph to get an idea of what this looks like. One flaw that I'll talk about more with drawing graphs is that what actually exists within this graph is what we call 3 different components. And those are sets of nodes and edges that are not connected to a larger set of nodes and edges themselves. So they form what we call subgraphs that are not connected. One of them in here is, where are we looking at? Like all the grays down here are actually one separate subgraph. But for some reason, it also placed an additional character down here, so it looks like they're all connected, when in reality, they're not. So we'll talk about visualization and graphs. There are a ton of caveats with that, and there are a ton of different solutions to that as well. All right, another common way of representing graph data is adjacency matrices. The best way to describe this is just to look at one. So here's an adjacency matrix. An adjacency matrix will have n rows and columns, where n is just equal to the number of rows, or the number of nodes that you have in a data set. So here we see that we've got all the characters listed. We've printed the first 5 rows and columns from this adjacency matrix. And with an unweighted graph, all that's going to happen is if a relationship exists between 2 nodes, that value in the matrix is going to be a 1. For an undirected and unweighted graph, this matrix is going to be symmetric. So you can fold it over the diagonal. So here we see there is a relationship between Finn and Gray. And the same thing is represented here, just the other way. NetworkX knows that if this occurs, it's an unweighted graph and it's an undirected graph. It's not going to duplicate this edge in any way. If it's a directed graph, this has different meaning, where a directed edge might exist between going from Finn to Gray, but if this didn't exist, there would be no returning edge going back the other direction. NetworkX has a function to read these in handily. It's the from numpy matrix function. And what we are going to do is pass it this, it's currently a data frame object we read into pandas. We're going to call the values attribute, which converts a data frame to a numpy matrix with the values contained in it. And we're going to pass that to this function. And this is the one time we're going to refer to it as something different, just so we can validate that these 2 graphs are the same once we've imported them. So the graph that we create from this matrix is going to be called GA-ADJ, GA adjacency matrix. One problem with loading it in this way is that you just have a matrix. You don't have labels for your rows and columns of that matrix. It's just the values. So here we're just printing out all the nodes, and you see that it's 0, just the number of nodes that we have. So we're going to create a label mapping. This is very similar to how we added in that attribute dictionary before, except the attribute is now going to be the node label and how we refer to that node. So here we're going to use Python's wonderful the dictionary and zip combo. So we're going to zip up the nodes, so just this list, and we're going to zip up the columns from our original data frame, which is the actual labels of the nodes. What it's going to do is just create a dictionary where the key is this index value as it currently exists, and the value is the actual named label from the data frame. Once we have that dictionary, we apply it with the relabel nodes function. We're going to pass it our graph and the mapping for the node labels. And we're just going to draw it out again here to verify that the labels were put on the graph. And there that is. So are the 2 graphs the same? Just to validate and sort of test that both these methods are going to return the same thing regardless of how the data is represented. One easy way to just eyeball that is just to call info on both of those and see if we get the same number of nodes and edges. It's very unlikely that we would import 2 graphs and they would be have these same values but actually be different graphs, especially since we know that we're dealing with the same data. That's sort of the eyeball way. You can see that when we pass it the original matrix we loaded in from, or the original graph we loaded in from the edge list. We still have 32 nodes, 34 edges, average degree of 2.12. When we pass it the graph that we loaded in from the adjacency matrix, you can see that we've got the same information here as well. There's a fancy math way that checks whether 2 graphs are the same. It's called isomorphism. NetworkX has a nice function to deal with that too. If you're dealing with more mathy representations of graphs or a lot of graph theory, you may deal with isomorphism. All we have to do for that is pass it our 2 graphs, and it will use an algorithm that looks at which nodes are connected to which other nodes, the degree, the number of edges, all that sort of thing, and is a more robust way of validating that we actually are dealing with the same graph object. All right, some quick gotchas here, things to look out for as you're dealing with this, these different imports. I came up with these as I was sort of writing this, and I was like, why isn't this working? And I was like, that would be a good, definitely a good thing to know, because this is kind of weird behavior. So here, what we're doing is we are printing out the edges of the Denny node. So if you just call, use dictionary notation on a graph and you pass it a node label, it will return all the edges of that node. So here we see when we pass it Denny, it's returning that Denny is connected to Izzy. and we've got this empty attribute dictionary right here. When we do that same thing on the adjacency graph, what happened was NetworkX automatically inferred that we had an edge weight of 1.0. So it's the same edge, it's representing the same information, but we just get this additional detail that the weight is 1 between them. With this undirected graph, it's implied NetworkX knows that the weight here is 1.0 if we don't explicitly tell it. But if you're trying to figure out like where these attributes came from when you imported an adjacency matrix, it may be because of how the data was structured in your original representation. One other thing that I've just briefly mentioned too, the source and target are ambiguously defined in undirected graphs. And the way that we're going to just test and validate that these are different is I'm going to convert the graph to an edge list. We've already verified that we're dealing with the same graph. But what NetworkX is going to do is use an algorithm to print out this edge list. And I'm going to sort that edge list by the first column, which is just the source in my edge list. I'm going to get both of those for the original edge list graph that we imported and the graph that we imported from the adjacency matrix. And I'm going to go through each of those lists and just say, if the source is different between these two sorted lists, tell me that, because that's kind of weird behavior. And we only have to go one edge before we notice that the sorting is different. So the second edge, indexed starting at 1, would be Addison and Kareev from the original edge list that we imported. And from the adjacency edge list, it's Adele and Chief. All that really means is that this edge occurs later in this edge list, and Kareev is the person who's the first person in that order. So again, with undirected graphs, source and target, when you're representing it as an edge list, are ambiguous. They don't have any meaning, so you can swap them back and forth. All right, and finally, we're just going to do a quick thing on exporting. So exporting graphs, we're going to export it as a GEXF file, which is the Graph Exchange XML format. This is a format that was created by the creators of the Gephi graph visualization software. If you're looking to visualize graphs, I strongly recommend using Gephi. If you're dealing with graphs, I would take a look at a download after this class and just start fooling around with it. It's a really awesome tool. But they created this format so that you could take graphs between different programs and store that information. So we're just going to write this. We're going to take the graph and write it to this GEXF file, store it as gagraph.gexf.
Unless the graph is super big, then
Maybe not. All right, so we've created graphs, we've added nodes and edges, we've imported graphs from several different representations of data, and we've, again, exported the graph that we're going to use for the rest of our analysis. So now that we've done sort of the stuff that we needed to do, we can do some of the fun stuff. The next chapter is on visualization. Go away, little header. Oh, I clicked on the slides, that's right. Wait. No, it's the notebook, yeah, okay. So visualization with graphs is a hard problem. I hope that goes away. Here's a cool graph of Disney's strategy. They had a meeting and they decided like what their corporate strategy was going to be in the 1930s and laid out this graph. This graph, the nodes are sort of like the different forms of media that Disney was dealing with at the time, and the edges were like how each one supports one of the other media formats. So here we've got, my favorite one is like merchandise licensing exploits films, and it leads to the theatrical films. So this graph was laid out by a human, and a human has several advantages over a computer in laying out a graph. One of the things that I like that this graph does is it uses these bendy edges. If those didn't exist, you would have a ton of overlapping edges and you would not be able to convey this information that's important on the edges, all the attributes of what that edge actually means. You also know as a human, you have some subject matter knowledge of which nodes might be more or less connected, so you can place them closer on the graph. One of the things that you want to avoid with drawing graphs is overlapping edges, right? And it's an impossible problem to completely avoid in a lot of cases. I mean, even in this graph you've got overlapping edges. But with a computer, it's one of the things you can optimize for, but you won't always succeed in doing. Okay, so for this notebook, we are just going to import NetworkX and matplotlib pyplot. And now this is a new function we're going to read in our GEXF file. It's going to contain exactly the information that we just imported in the last stage. And I'm just going to print out to prove that we are dealing with the same graph object GA here. So again, 32 nodes, 34 edges. We're good to go. All right, so mostly this is going to cover plotting with matplotlib. There's a lot of connections between NetworkX and matplotlib that make it easy to plot out. You have some customization available to you. The cons, of course, is it has that classic matplotlib look to it. It's not interactive, which a lot of times graphs contain very dense and detailed information that you need an interactive visualization in order to fully understand. And there's few layout options. So when I say layout, it's this concept that we talk about in visualizing graphs where it is a computer optimizing where it's going to place the nodes and the edges. So those algorithms are called layout algorithms. So the easiest way is just to call this draw function. We've seen this a few times already. You pass it the graph. We also are going to have this argument with labels to show the labels that we have with our graph. You may want to turn that off with huge, larger graphs that are going to have a bunch of text labels on there. So we see our graph. This one, we do see one of the components. So we see that this is a separate component up here, Tucker, Bailey, and Ben. That brings me to my next point. Graph layouts are random, depending on initial conditions. So on the plus side, you can rerun a graph algorithm until you get a good layout. On the negative side, it makes it very hard to replicate the same layout. You'll deal with this problem a lot if you're in graph visualization. A lot of times, NetworkX isn't so good at illustrating this, but other algorithms, when you use them, they will converge to a same sort of graph structure, but you may have to deal with like rotating and fine-tuning some nodes once you've laid it out to get it exactly the same as a previous layout. Okay, so detailed plotting, got a big chunk of code here. These are some matplotlib options, so we're just going to increase the size of our figure. We're going to turn the axis off when you begin to use matplotlib. It automatically adds an axis on there, but we don't actually care about what the XY coordinates of the nodes are. We're going to save the layout as this layout variable. So what we're going to do is we're going to apply a circular layout. So we're going to call that circular layout method on our Gray's Anatomy graph object. And that's important because we need to pass that to the rest of our functions here. So if you're not going to use just the plain draw function, what you do is you make these calls to these more complicated functions that add in each part of the graph as a layer. So first we're going to draw the nodes. To draw the nodes, we pass the graph, we pass the layout to this POS position variable argument, and we're going to add some other options. So we're going to increase the node size to 500, and just for fun, we're going to add a transparency alpha of 0.8. There's another set of options that you can use with this to customize things about the nodes to get a good visualization here. Once we've plotted the nodes, we're going to plot the edges on top of that. So same sort of style. Here we're going to change things about the edges. We're going to increase the width to 3. We're going to make them dotted. We're going to make them orange. We're going to have a really ugly graph because of this, but I just want to show you some of the options that you can pass to this function when you want to change some attributes of the edges in your graph. And finally, we're going to draw the labels. Same style. The only thing we're going to change here is we're going to up the font size so that it's easier to see. And we're finally going to call the show method on our plot. That's what it looks like. This graph is not informative. The circular layout is not really good at retaining a lot of information about the graph. You lose a lot of stuff because it's just not taking advantage of the structure of the graph. It's saying, give me all the nodes. What size circle do I need to plot all these nodes? Let's just plot all the nodes and plot all the edges. It's not taking advantage of which connections exist or trying to prevent overlapping edges. It's really just a way to get it on the screen, basically. But I did that just to show you that there are these different layout options within NetworkX. For the rest of the presentation, we'll be using the spring layout, which is the default when you make calls to draw. Spoiler alert, up ahead, if you're not caught up to like whatever season they're on of Grey's Anatomy, people die. I think it's one of like the calling cards of the show, because when I was doing research on YouTube, like the top 5 recommended videos were like top 10 saddest deaths in Grey's Anatomy and like top 5 like worst, most emotionally impactful people dying. So apparently it's a theme of Grey's Anatomy. If you watch a season finale, you can almost be guaranteed that one of the main characters will die. So that's an attribute that we care about. We want to see where the dead people are in our network to see if the writers of the show are writing out people that are important in our relationships here. So this is just a dictionary of whether each character is dead or alive. This in the presentation came before that, so sorry if you're not caught up on Grey's Anatomy. So we're going to use that set node attributes method again. We're going to pass it the graph. We're going to add this attribute to each node as status, and we're going to pass it the dictionary of just dead or alive. What NetworkX expects when you're plotting is a list of hex colors that match up to the ordered set of nodes that you're dealing with. So I just created a little helper function here. I'm not going to go through in a ton of detail, but basically what it does is it takes in the graph and the attribute that you care about in the graph, and what it'll do is return a color attribute for each node in your graph, depending on the original attribute you care about. So here all it's going to do is say, I have an attribute dead or alive. I need 2 colors to identify the difference in that attribute, so I'm going to give you back the list of hex codes that represent those different colors for each node. So we're just going to save that as node colors. We're also just going to save the color mapping that it came up with, so we can see the hex codes for each color and the palette itself to visualize which colors are what. And then we've seen this pattern before. The only difference here is we're going to use this node color argument when we're plotting the nodes, and we're going to pass it that list of node colors. So here's the big reveal. A lot of important people are dead. I believe it did alive is blue, green is dead here. So O'Malley, sorry pal, he was connected to a lot of characters. He has since passed and been written out of the show. Lexi and Sloan, I think the only dead couple that existed. We've got Adele and Ellis over here. A dead, well-connected couple that is no longer in the show. Sorry, Derek is gone, Denny's gone. A lot of people in this component no longer with us. So this is a pattern that you will do a lot if you're visualizing graphs. Attributes can contain a lot of important information about the nodes, and oftentimes you'll want to visualize that. And the nice thing about graphs and networks is that the visuals are really easy to make inferences out of. From here, we're able to see that they killed off a lot of important characters if we're looking at it from the perspective of what romantic encounters they had. So visualization is a really nice tool when you're dealing with smaller graphs to plot it and take a look at what information you can glean about those attributes. There are several other visualization options. If you want to take a look at these links at the bottom, I've already talked about Gephi a little bit. That's one tool that I use the most. But there are several other options for plotting within Python or using other tools to plot as well. All right, I'm done gabbing. I'm going to pass it off to Rob. He's going to talk about centrality and importance within networks.
Rob, you want to check and make sure everybody's got access to the Jupyter notebook. If not, I put it on Twitter, so if you go to GXO, there's a link out there. It's also on the Slack channel. Thank you. But anyone you have trouble following along or have questions, it's always good to ask a question.
Yeah, any questions while we're like halfway through the talks and we've got all the infrastructure then to like learn stuff about the networks? Good? Okay, I think I'm gonna, so Peter was very good about how everything in the notebook was one-to-one. My notebooks are a little more chaotic, and so I'm gonna stick to the slides. We can go back to the other ones. There's just extra information that I didn't actually put in the slides that are in the notebook. So we'll see how this goes, and if we have to switch back and forth, we'll do that. But this is, I'm glad Peter did the first half, because now we can get to like the really interesting stuff about learning about the network that we took so much time to kind of build up and set up. All right. So first I'm going to be talking about, oh my God, that gets so small. Let's see. That's a little better. Okay. We'll see how this goes. All right, so we're now going to move on to our first applied kind of topic, which is the idea of centrality. Centrality is just, it kind of defines itself, right? It's trying to figure out who are the most important characters in my network. And so in the context of the romantic relationships, that could actually mean a lot of different things, right? Like what would that mean for the Gray's Anatomy data set? And what's nice about all these centrality measures is they all kind of try to capture a different component or part of this idea. And so we're going to go over 4 popular ones: the degree centrality, the closest centrality, the betweenness centrality, and lastly the eigenvector centrality. And they'll each tell us a little something different about this graph. This is just, if you're following around the notebooks, it's just what the libraries were doing. It's just NetworkX and matplotlib, and then reading in that graph object from earlier that we created. All right, that's not bad. Okay, so the first measure we're going to go over is degree centrality, and if you remember from the beginning, the idea of a degree is just of a node is like just the number of edges it has. So for example, this one here on your right has a degree of 5 because there are 5 connections to it. Likewise, this one on your right has a degree of 2 because the central node has is connected to 2 other nodes. In the context of our Gray's Anatomy data set, this means that this character over here in the center would have had relations with 5 different characters in the cast, and the one on the right would have 2. This makes a lot of sense, right? A measure of importance, you might imagine that people with a lot of connections would be really important to a graph, right? It's like if we were thinking about Twitter or something, those people who have tons of followers, maybe celebrities and stuff, are really important people because they can get their message out to a lot of folks. And so this is a really intuitive measure of what actors are important within a network. To calculate this thing, it's really easy. You just take the degree, which we've calculated over here, and divide by the total number of nodes. That's it. We'll kind of see how this plays out in practice. So basically, all you have to do to get the degree centrality once you have this graph object is just call the method degree centrality and then add in your graph object and then let it run, and boom, there we go. The degree centrality for all the characters in our network. Now, this isn't super informative, just kind of as it is, because they're listed alphabetically. We probably want to know who are the most important, right? So we're going to sort this a little bit, and so these are the top 5. These are the top 5 characters that have the highest degree centrality in our network. So starting off, actually before I start, how many people are like familiar with Grey's Anatomy? I'm just throwing around characters right here, and okay, so we have like 2 people in the audience. Okay, so this is cool. All right, we'll go. I'll get out of these notebooks a little bit and just, at least have a picture to go with, like, who these people are, at least the top ones. Okay, so the top person here is Alex Karev, and he has a degree centrality measure of 0.225, 8 something something, going out to like 14 digits. What's easy about the degree centrality is that really what it tells you is it's the percentage of the total network that this person is connected to. So what this is basically saying is that Alex is like hooked up with a quarter of the cast of this show, which is kind of amazing. And then he's kind of by far the most. Sloan is next with about 16% of the cast, and then it kind of goes down from there. So just to give this dude some credit, we'll look and see who this is. Give a little bit of context. Alex Karev. Yeah, this dude. Yeah. Yeah, this guy. So, yeah, you can get it, right? I mean, yeah, good-looking guy. Seems like he's, plays the field a bit. Heartbreaker, all that stuff. So that's Alex. In addition, what's nice about degree centrality in addition is that it actually maps so easy to just the degree. So if you actually want to know how many people this Alex has been with, you can just do this almost the exact same syntax, but just on the degrees as opposed to the centrality, and we can see that Alex has been with 7 other characters. Okay. So yeah, that's a really intuitive degree centrality measure. Some of the other ones, though, try to capture some other things. For example, one of the downfalls of degree centrality is that it only captures relationships of their immediate neighbors. It doesn't capture anything else about their context within the larger network. And so closeness centrality is one of those metrics that tries to tease at that a little bit. Essentially, the closest centrality, the best way to think about it is kind of like what the average distance of, it kind of like sums up the average distance from that node to every other node in the network. So the person with the highest closest centrality will have the lowest average distance to any other random node in the network, right? And the way that you kind of calculate this is you kind of you sum up all the shortest paths from the one node to every other node, and then you divide it by the total. You divide it by the total number of nodes, and then you can take the reciprocal. So are we sort of familiar with the idea of shortest paths? I don't know what people's background. Okay, so yeah, the shortest path is well, it's really in the name, right? It's really the shortest way to get between 2 different nodes. So for example, with our example up here, if I wanted to say, and for this weighted graph, what is the shortest path between nodes A and B? I'll say it. So if we're looking at it from a weighted thing and we're taking into account the weights of the edge, it would be ACB, right? Because there's only 2 different ways to get from A to B. You got ACB, which is 3 plus 2 plus 1, a total of 3. And then there's the direct one from A to B, which is a weight of 4. So basically, what you're doing in the denominator here is you're taking for a given node. Let's pretend this instead of U is A. We add up all the shortest paths between A and every other node, and then we add those up, and then we, as a denominator, and the numerator would just be the total number of nodes, which in this case would be 6. So not too bad, but it's a little more computationally complex because you have to kind of make these connections between all the nodes. All right. So what I love is that the syntax is like exactly the same and super easy to get these centrality measures. If you can, as you see, these are like the exact same slide, except for instead of degree, you put in closeness instead. So we do the same thing. We get our list, but let's look at the top ones and see if we can interpret this a little bit. All right. So so as you can see, we actually have different people here. As opposed to with degree centrality, Alex is kind of leading off the charge. Now with closest centrality, we have Torres, who's also an interesting character, and because no one watches Grey's Anatomy in here, I'll bring her picture up too. Callie Torres? Torres? Yeah, there's Callie. Yeah. So there's Callie Torres. So in terms of interpreting this, what does closeness centrality mean in our particular network of relationships, right? So we said closeness is kind of like the average distance, right? And so I was thinking about this, and the best way I could think about how this could be relevant is if the creators or writers of Grey's Anatomy had this very, very dark like story plot where one of the characters got like a infectious disease or an STD, and they watched it spread across all the other characters. So those with highest closest centrality would be the ones that would be the absolutely worst person to start off with, because they would theoretically be able to reach everyone else in the network the fastest. So if we wanted to totally, very darkly spread infectious disease across this entire network, Torres would be the one that you'd want to target. Alex, to be fair, is also on this list because, well, you know, he's just connected to everybody. So, oh, and then to kind of give you a more interpretive kind of measure, instead of just having this, this bounded value between 0 and 1. To actually look at the average distance, you take 1 over this value here, and this is essentially the average distance. So this is telling us that like about 3 is Torres is connected to every other a random node like by 3 1/3 hops. Yeah. Yeah, kind of like yes. So
I have a hard time visualizing the difference between the closeness and
yeah, there's actually a great. Well, we could do this now. I think. I don't know. Can you see these networks well, or should I pop over to the notebook to make them a little bigger? Okay, for now. Everyone can. Okay. So what's nice is that this is actually on the centrality page of Wikipedia. So if you don't find it here, it's very easy to find. This is given a common data set. On the same data set, how basically the centrality measures for a bunch of different centrality measures, and kind of how the different ones show a various importance. So for example, what have we done so far? Degree. This one down here is in D, is the degree centrality. So as you can see, the ones that are really well connected, like really dense, are darker red. So there you can see this one is really kind of connected. There's a bunch over here that are super connected, and that's kind of how you'd visualize it. The ones that are higher would be darker red, and that's one way you can do it. For example, what do we do? Closeness. We did closeness, right? So closeness centrality, I believe, is B here. It's looking at, and so this one is looking at like essentially, if you had to like plop down, yeah, this is kind of like the patient 0 kind of thing, right? If you plopped it down here in the red, it would kind of spread out, in this case, kind of sort of uniformly from it, and that's why the centrality measure is, that's why closeness kind of looks like the way it does here. Because these ones in the edges probably won't get, it'll take a long time to get there, but these ones in the front will get there sooner. Does that sort of make sense? We'll talk about, we'll come back to this, especially with eigenvector, but we'll also talk about, this is a Petunis one, but we'll talk about that in just a second. Does that help a little bit? Okay. Yeah. All right, betweenness. This is kind of an interesting one. A very convoluted one to try to work into our data set, but it's like super important for other topics. Okay, so we've got degree centrality, we've got closeness centrality. Now we've got this idea of betweenness. Basically, betweenness measure, those with high betweenness centrality, are those that act as like bridges or brokers in your network. So I think this illustration here is really nice of telling kind of like iconic what an iconic like high betweenness centrality node would look like. So this one A, suppose for example that the only way that you could get between one group of nodes and another group of nodes is through an existing kind of pair, right? A here would be really high betweenness because it connects all these this kind of connected dense red group and this connected dense blue group. So going back to our karate club example, there's actually a lot of community detection algorithms that use kind of this idea where they just chop off the ones that are where the edges that are most betweenness, and those things that are left are these kind of like inherent community structures. And so the way to calculate this, does that make sense? I always have a hard time deciding betweenness. Okay, so the way you calculate this is that you instead of so just for any single node, right? Thinking about A, what you would need to do is you would need, just to get the betweenness centrality of this single node, would need to calculate the shortest path between every pair of nodes in your network, and that would be your denominator. And then of all the shortest paths, determine how many of those actually contain your node of interest. So between this node and this node, between this node and this node, between this node and whatever, how many of those is A part of that shortest path? Kind of intuitive, but again, like very computationally intensive. All right, so we've seen this before. Literally, it's, yep. Instead of closeness centrality, degree centrality, we use betweenness. We're getting them, and we'll look at the top 5 again. Okay, so the top 5, again, they have some of the same people, but there are some new ones. For example, we have a new kind of top person in terms of centrality, Sloan, which, again, for some context, I'll get Sloan. Gray's Anatomy. Yeah, Mark Sloan, this guy. He dies. Yeah, Alex is still alive. I think Torres is still alive, but yeah, Sloan at some point doesn't make it. You gotta kill off the characters we love, right? So, yeah, this guy is a major broker in this network. But in terms of relationships, what does that really mean, right? I had to come up with a pretty convoluted example for this one, but it's kind of interesting and kind of fun. So let's assume that I'm a character in Grey's Anatomy, and the only way I can start a new relationship with another character in the cast is that I have to ask permission from one of their former lovers. And the only way that I can get to that, I can contact that former lovers is through my former lovers. So we got these like pathways that you can connect with new people. Basically, the people with the highest betweenness centrality are those ones that could have theoretically the baddest like veto power in the network. They can just say, "Oh, you wanna go?" No, and they can just cut it off. And they're so central with their previous connections that they could kind of shut it down real quick. So that's the power that Sloan has in this hypothetical situation I came up with. Yeah, it works better with other type of networks, but you could even force it onto our example. All right. The last one. Okay, and I guess to a little more context, this is a betweenness centrality. Yeah, so this you can see that this one in the center is kind of a major broker between different parts of the network here. So if you kind of a lot of people have to go through the center node, and so that's why it's really central. Okay. All right, so the last one we're going to cover for centrality, this is probably our longest section, so thanks for bearing with me, is eigenvector centrality. This one's actually super interesting because essentially the higher the eigenvector centrality is, nodes with high eigenvector centrality are connected to many other nodes that are also well connected. So that's kind of like the eigenvector centrality tries to get at this concept of it's not just quantity, but also the quality of your network that's really important. Where quality would be, in our case, the number of connections you have. So basically, you would have a higher eigenvector centrality if you've been with other people who have also been with a lot of other people. You know, you kind of stick to your type in that sense. You know, the more promiscuous people, maybe with more promiscuous people, they'd have high eigenvector centrality. And you can kind of see from the contrast here between the degree and eigenvector that they're kind of the same, but also sort of different. As you can see, since there's a lot of red density here, that's also where it's high eigenvalue centrality. So the ones that are really highly connected and high degree are also going to be high here. This one, even though there's this one node that has a high degree, because it's not connected to other nodes that are also high degree, it is not as relevant. So there you go. Visually, boom. These other two we won't talk about, but they're in the appendix. It's the harmonic and the cat centrality. All right, we do this again. And yeah, so this one I switched up a little bit. So instead of these, I won't talk about the math. Essentially, these numbers here is the eigenvector associated with the largest eigenvalue of the if you transform it. But these are really hard to interpret because they're like, some of them are super small, right? This is 5 to the negative 17th power, right? And so to scale them, basically, I had the max value, the one with the highest centrality, and just scaled them all from there. So Alex, who's our top starter again, is a 1 because he's, it's just him divided by him, and then the others kind of fall into place. So yeah, this is kind of telling us that, again, that Alex not only has been with a lot of people, but he's also been with a lot of people who've been with a lot of people. So that's in itself is kind of interesting. And you can see that a lot of them are kind of the same, but there's some that are will probably be less relevant than degree. All right. So that's the section on centrality. There are other measures of centrality that try to tease out some other things. We can talk about it later if you want, but yeah, but I'll keep this moving so we can have time for questions later. We're next going to talk a little bit about this idea of link prediction, which is super interesting. Let's see. Community. Oh yeah, here we go. This is a short one, but like super, in my opinion, like super interesting. Gift it. All right. All right. How are we doing? Okay. All right. 2 more to go. Next, we're going to move on. So first, we talked about centrality, right? Who are the major players in our network? Next, we're going to talk about link prediction. You might think that this basically tries to address the question of, given a snapshot of a network, can I predict which future relationships are going to happen just by a current snapshot of our network, right? This illustration does a way better job of describing what I'm talking about than me trying to. This is us now. Can we predict what relationships are going to be there in the near future? Easy, right? Sort of. The thing, though, is that this isn't, at least to me, when I thought about this problem, it wasn't entirely clear about how this actually works or why this should actually happen. Why should a structured network help determine why a future relationship would happen? And so we'll go over 2 examples of this in the coming slides. This is the same stuff. We're adding libraries and uploading our data. Okay. So as I said, basically all the measures that I'm familiar with link prediction basically make the assumption that nodes that are pretty similar in some way are going to be ones that aren't connected are going to be ones that will be connected in the future. So Jacquard coefficient in this case is looking at sets of nodes that have it's actually looking at common neighbors between pairs of nodes. So this is pretty intuitive, right? If let's say Peter and I are different nodes in this network, I've got a bunch of friends, Peter's got a bunch of friends, and we actually have a lot of friends in common, but we haven't met yet. Chances are, because we have a lot of people in common, and maybe we share a lot of interests together, maybe we'll meet each other at like PyData Carolinas or something, right? And you know, we'll make that connection. They're saying that because we have a lot of things in common, a lot of neighbors in common, we'll probably be matched up together and be a future relationship. Looking at the math, really us is doing is looking at the intersection of two sets. So this purple part in the middle over the union of two sets. So which is the entirety of these overlap. This Venn diagram really. So these are all the friends I have just to me. These are all the friends Peter just has to him, and these are the friends we have in common. So we have a high number of friends in common. We have a high Jacquard coefficient. This is predicting that we're going to be friends in the future. To do this, again, super easy. Once you got all this stuff into a graph object, you just call Jacquard coefficient. You add in your graph object, and because this is a generator, I'm saving it. I'm running it through and saving it to a dictionary just so we can reference it later. And then we're going to sort it. So these are the top 10 pairs in terms of the Jacquard coefficient. So this is kind of interesting. Can anybody tell me an interesting thing about these top predictions? I don't know. This might be really hard considering not many of you have been watching the show and probably are familiar with these characters. But does anyone want to venture a guess? Okay. What I found really interesting is that all the top 10 are same-sex couples. You might be thinking, and I actually I don't watch the show a ton. I just kind of watch it when my roommate has it on. So I was like, is that like, what's going on here? And actually, most of these characters, at least on here, there are some, there are some couples that are bi and gay on the show, but none of these characters are in terms of their past sexual history on the show. So what's going on here, right? What is this really? Why is this doing this? Well, if you think about it, it kind of, from like a math standpoint, it kind of makes sense, right? Like, let's say that, again, we'll use Peter and I as an example. We have also, in addition to having a lot of common friends, we also have been dating the same people forever, right? And so we have a lot of ex-lovers that are in common. So you might think, well, we got a lot in common, like, we have all these ex-lovers, like, it just makes sense that this is going to happen. We obviously have the same taste, right? Right, high Jacquard coefficient, same number of neighbors overlap, right? You can see why in this this particular example, it doesn't make a lot of sense. And so this is the great thing about having real data, like, and being able to, this is why we all have jobs as, data scientists and analysts, right? Like, just, you can do this stuff, but if you don't kind of interpret it later, you get in a lot of trouble. It might not make a lot of sense. And so this particular one is probably not that effective for our particular network, but it can be really useful in other situations.
Is there an easy way to run that over a bipartite graph?
Yeah, so we were thinking about that. One way of thinking about this is Nathan mentioned that we could think about this as a bipartite graph, right? Where the two different there's actually two different entities. There's males and females, and it gets a little more complicated probably because there are people who are bisexual on this show, like Torres. But I think we could. We didn't run it here because of time, and but it's something that I think I'll probably add to the notebook later if I got some time. It'd be really cool to look at. Yeah, that's a great suggestion. Another question. All right.
I'm not entirely familiar with a lot of the graph type functionality.
Yeah.
Is there any mechanism to take advantage of attributes of nodes
Mm-hmm.
so that you can definitively put in, well, Steve and Hank, or Hank and Denny are heterosexual,
Right.
and so
Right.
it eliminates them from the graph completely?
Mm-hmm.
How does that work?
Yeah, so the question was, can you use essentially can you use attributes of a node to like condition or on things so that you get a smaller subset and you take into account these the attribute of the nodes and so the edges and stuff. I think there are most of the ones out of the box probably don't kind of do that, but one thing we were planning on doing and is sort of the notebook is that I added extra information attributes about the gender and kind of past sexual orientation of the characters, and I was just going to kind of look at the ones that are opposite sex to see if those are interesting. That's kind of like a very naive way of doing it. There's probably more.
You can add like in a dictionary or something like you have
Yeah.
build attributes to a node
Mm-hmm.
and you check,
Yeah.
slice off the first attribute of each to check or something like that. Is that what you're?
That's probably my first. That would probably be what I would do. I don't know, Peter.
There are implementations of Jupyter index that take into account those other characteristics.
Yeah.
And I'm sure you could invert that and say, yeah, if these two are not the same, add more weight or less weight
Yeah.
to this relationship.
Yeah, people. What I love is that this is a super active community too, and there's a lot of folks who have thought about weird edge cases like we have, and have write dissertations on stuff on it. So I'm sure it's out there, and I think some implementations actually do have it right out of the box. All right, so we're going to look at one more. Link prediction algorithm, and then we're going to get into communities. This one's actually super interesting and probably more relevant to our network. This idea of preferential attachment. It kind of mirrors this mantra of the rich getting richer. In our network, it'd be the people who are more connected, either because of their past connections or because something maybe natively inherent to what they're doing, will allow them to get more. Those people who have more connections will be the ones who get more connections in the future, right? So maybe in our example, if Alex is like really handsome, and he's kind of has a reputation out there, and people are like, oh, this is like a low risk thing, like everyone gets with Alex, it's a rite of passage being on this damn show, whatever. There's a chance that like Alex would also be would be the one. It makes sense that Alex might be one in the future to have a future relationship, as opposed to someone who is kind of like in a monogamous relationship or not really getting themselves out there. Okay, and so the math for this is actually pretty straightforward. All it really does is say, what's my degree? What's your degree? Let's multiply that together. That's it. That's really all it is. So all it's doing is matching people who have high degrees together and saying like, yeah, this will work, right? You're promiscuous, I'm promiscuous, this is going to happen. That's really all it's saying. So here's what we do. Same deal. And then we've got our top matches here. And some of these, I mean, the first one is kind of hilarious. Kind of like the two playboys of our network, Sloan and Alex, are kind of matched together. And yeah, who knows? Maybe those two would get together. They seem like they get together with a lot of people. And so they have a very high match together. But the subsequent ones, there's actually some pretty like valid pairs here, I thought. For example, the second one, the most highest predictive one, is a match between with Meredith, Meredith Grey, our main character, and Alex. And actually, I was like, well, I'm surprised this hasn't happened yet. So actually, last night I went and looked up on Google. I think all I did was Meredith and Alex. And boom, the first one is this result from earlier this year in June. Grey's Anatomy boss talks Meredith and Alex's potential romance. So boom, our predictive, our algorithm like made it happen. Like this is beautiful, right? This is exactly what we were hoping to happen. Actually, we don't need, this is going to take forever. There's probably a crap ton of ads. Oh, look at that. That is heartwarming. So yeah, will these two get together in season 13? I don't know. But the data says maybe, yeah. So this one actually, even though it's very crude, it's a very, very crude measure, does kind of tell us some interesting things about the network. This is the wrong notebook. This is community. Yeah. Yeah, and there's some really interesting ones here. yeah. Christina Yang and Alex, maybe. We're not going to go into all these, but yeah, some of these are super, super interesting. And if these characters weren't dead or already written off the show, yeah, they probably would have happened. I'm thinking. I don't know. I'm not a writer for Grey's Anatomy, but that's just my hunch. Okay, so these are some other link prediction algorithms. They're all kind of try to tease out this idea of nodes that are similar but not currently connected are going to be connected in the future. And we can talk more about these after the talk if you're interested. But they're here for reference as well. Okay, so that's the end of my spiel. I'm going to hand this back over to Peter, and we're going to do our very last topic. Oh, but before that...
10 minutes? All right, let's do questions instead.
Oh, we got 10 minutes left? Okay, let's do questions. Sorry, I probably ran way over my time.
Yeah, so there is an additional notebook on community detection if you are interested. We won't go over it, but community basically answers the question, where do I belong? And in which groups of nodes am I more connected compared to other groups of nodes? There's a whole notebook there. There's also an appendix with some other references and resources for you guys as you continue your adventure into social network analysis with Python. I think now would be a good idea to open up for questions that you guys might have, and we'll do our best to answer them together.
My favorite part is running around.
Thank you. It was a very interesting talk. You spoke a lot about time, but never explicitly looked at your network progressing through time. You have like patient 0, but hey, this guy's dead. He's not passing anything on right now, unless it gets really weird.
Yeah. Time is an interesting variable to add to graphs. And it's an active area of research within network theory and social network analysis. One of the things that's really helpful with time as an attribute is that it answers a lot of the issues that happen when you deal with larger graphs. I just read a paper where they were dealing with detecting communities in like super massive graphs. And a lot of times when you deal with large graphs, getting past like 100 or 200 nodes, you get what's called the hairball effect. And it just like plops a bunch of garbage on the screen. Everything's so connected that it's really uninformative. And what these people did was looked at how the graph had changed over time. And it was people who were calling each other on the phone. And what they did was like when they added that time dimension, they were able to see like which clusters and which communities of people were active in the graph, which was something that they couldn't see as a whole. So there is a whole nother dimension of time and algorithms to treat time in graph analysis.
So you're looking at graph at time t and graph at time t plus 1. Like more explicitly, how are you doing that with NetworkX?
Yeah, I don't know that NetworkX. I haven't done a lot of time-bound or dynamic graph analysis. I don't know that NetworkX has the capacity to handle that. I know there are 2 other libraries that I would recommend if you're interested in pursuing it more. There's the iGraph library, which if you're familiar also has an R version as well. And there's a library called GraphTool. I don't know about their capabilities to deal with time-bound data.
Who's getting some?
A similar question, if you took it from the most recent data from Grey's Anatomy, if you looked at like at the end of season 1 and then did some of these closeness vectors to see if like you actually got results of people that had future relationships. It could just be fun.
Yeah, it would be awesome. I think exactly what Rob ended on and sort of like predicting which characters might get together, it would be cool to do like rebuild this after every season and sort of like make our predictions for the next season.
I mean, that's what they did in the original paper, right? To validate the prediction paper?
Oh yeah, there actually was a good, there's a paper that goes over sort of like the robustness of each of these link prediction algorithms. I can put it out there. And what they did was like they looked at a collaborators network. So if you're familiar with archive.org, it lists all these preprints of papers, and people use that for network analysis a lot of people who collaborate on papers. And they validated these link prediction algorithms by just taking 2 different time subsets of that and saying like, here's 3 years of data, let's run link prediction on it, and then let's validate which links actually occurred in the next 3 years and rated the algorithms off of that. So yeah, it is a good idea to include time as sort of a validation measure as well in your data.
Other last comments, questions? Who's got question number 3? No one?
Question number 3, go for it. We got one over here.
Yeah, thanks.
very nice talk.
Thanks.
And I have one question. So, what's the time complexity for to compute different metric of the centrality for the graph? So,
Yeah.
how large graph can we apply this centrality?
Yeah. That is a very good question and an issue we're running into a lot now at work. The complexity for different centrality measures differs. Eigenvector centrality is pretty quick because you're just calculating like the matrix decomposition. But between a centrality, you literally have to look at every pair of nodes. That's really computationally intensive. Handling large graphs in NetworkX is really hard because it's written purely in Python, so it can be a bit slow. It will still always run, just depending on how patient you are. But I've run into issues where I've had graphs of maybe over 10,000 nodes that I wouldn't run centrality measures on them just because it takes so long to do. The iGraph package and graph tool have some bindings to some C++ libraries that really speed up that computation and are meant for handling larger graphs. But I would say like beyond maybe even 5,000 NetworkX, you're probably going to want to start to look at alternative tools for handling graphs that large.
Okay, great. Thank you.
Yeah.
Excellent. So if there's no more questions, I want to thank Rob and Peter. Thank you guys so much. This was great. So there'll be a 15-minute break. Yeah, clap.